Capacitor Geometry and Dielectrics. The area of the capacitor is the surface area of one plate and is represented by the letter A. Both plates have the same area. Okay? The distance between the plates is represented by the letter D. For parallel plate capacitors, the capacity to store charge increases with the area of the plates. You can imagine if you have a bigger plate, you have more room to put charge on it. It will also decrease as the plates get further apart. That's a little more subtle, and we'll leave that for later. So basically, the capacitance is directly proportional to the surface area of the plates and inversely proportional to the distance between them. Since they're both proportional, we can combine them and find the capacitance is proportional to the area of the plates divided by the distance between them. And recall, D is very, very much smaller than A. Here's a little math and physics trick. Once you have an equation that involves a proportion sign, you can replace that by an equal sign and some kind of constant, known as the constant of proportionality. For capacitors, it has been theoretically predicted, which is good, and even better, experimentally measured and verified that this constant of proportionality is called the permittivity of free space. This shows up in many other places, but this is the first time we're introducing it here. And it's symbolized by epsilon 0, and it's 8.85 times 10 to the minus 12 Coulomb squared divided by Newton meter squared. For parallel plate capacitors, C proportional to A over D becomes capacitance is equal to epsilon 0 A over D. And you can see from this, the greater the surface area, the greater the capacitance, and the closer the plates get together, the greater the capacitance, and epsilon 0 is a constant. A capacitor has plates of area 0.015 square meters separated by a distance of 0.2 millimeters. What is the capacitance of the capacitor? The area is given, and that's in the right unit, square meters. The distance between the plates is in millimeters. We have to turn that into meters. So that's 0.2 times 10 to the minus 3 meters. But then we'll move the decimal to the right, decreasing the power to 10 to the minus 4. So we have 2 times 10 to the minus 4 meters. You also could have just used it like this, 0.2 times 10 to the minus 3 meters. We have epsilon 0. You don't have to memorize that. That will be on your formula sheet for any exams you take. And we use our equation for capacitor geometry. Epsilon 0 A over D. Here's epsilon 0. Here's the area. And here's the distance between the plates. And we get 6.64 times 10 to the minus 10th farads. A capacitor is being designed with plates of area 8 times 10 to the minus 3 square meters. How far apart do the plates need to be so that the capacitor has 12 picofarads of capacitance? The cross-sectional area is 8 times 10 to the minus 3 square meters. That's good. Capacitance is given in picofarads, so we have to convert that to farads. 1 picofarad is 10 to the minus 12 farads. Here's our permittivity constant here. Here's our equation for capacitor geometry, but we need to solve for D, the distance between the plates. So you cross-multiply the D and the C, and you get the distance is epsilon 0A over C. Substitute in our givens, epsilon 0, A, and here's your capacitance right here. And the distance between the plates is 5.9 times 10 to the minus 3 meters. Let's dig a little deeper into the properties of capacitors. Let's say you have a fully charged capacitor. You have the battery on it. You've separated as many electrons as you can from up here, and we're in a stasis. We're at equilibrium. Let's disconnect the battery, take him out of the circuit, and change either the area of the plates or the distance between them. Don't ask me how we're going to do that from an engineering point of view. We're just doing concepts here. What do you know about the total charge on the capacitor? Think about the conservation of charge and how charges were flowing in this system before going to the next slide for the answer. The charge remains the same. There's no place for it to go. Charge needs to flow through a conductor, and once the battery was disconnected, once it's not here, there's no conduction path, so no charges flow. Charges can't flow between the conductors because air is a great insulator. So the conservation of charge tells us that the charge you start with is equal to the final charge. That's why you should never handle a capacitor if you don't know where it has been. It might be holding a charge. It can hold a charge for a long time. And if you were to somehow put one finger here and one finger there, which would be very easy to do because capacitors don't have to be that large, you will discharge all those charges through your body into the ground. That can be very dangerous. Imagine you have a fully charged capacitor. This time you're going to keep the battery connected and somehow change either the area of the plates or the distance between them. Again, don't ask how we're going to do it. We're just trying to illustrate some concepts here. What do you know about the new voltage between the plates? Before going to the next slide for the answer, here's a hint. Think of the conservation of energy. The voltage remains the same. Voltage is the amount of energy delivered to each charge as it passed through the battery. Since the battery is still hooked up, it maintains the same potential difference between the two plates. That's because energy is conserved regardless of how you change what the capacitor looks like. Since the energy stays the same and voltage is the energy per charge, the voltage will stay constant. We can increase capacitance, which would be a good goal because we can then store more energy in the capacitor by inserting a dielectric into the gap between the two plates. Instead of just air, we're going to put in an insulator where it's a specific kind. The atoms in a dielectric, here are the atoms, they're slightly polarized. What that means is the electrons are not evenly distributed throughout the atom or molecule, whatever we're putting in here, so that one side will be a little more positive than the other and the other side will be a little more negative. They'll still be neutral. They'll just be this little shape where this side will be negative, this side will be positive. Before we charge the plates, if we just put the dielectric in here, the atoms, their plus and minuses, are all pointing in random directions. So as a group, the dielectric is unpolarized. Each atom is slightly polarized, but as a group, on average, you have a neutral dielectric here. You don't have one side more negative or more positive than the other. Now we apply a voltage to the two parallel plates. What's going to happen is we'll have a plus charge up here. This plate will be positive. Okay. This plate will be negative. What is that going to do to all the atoms in the dielectric? They're going to line up. You can see here the negative of this atom or molecule is more closely attracted to here. Same with this guy. The negative gets attracted to the top. So I have a polarization here now. All these little atoms line up. So if I have a positive here and a negative here, what does that look like? That looks like an electric field in that direction. So what have we created here? We have an internal electric field generated by the dielectric, and it opposes the applied electric field from the battery. The strength of this field is going to depend on the material of the dielectric, how polarized the atoms were in the beginning, and how easily they respond to an external field. So just quickly summarize, positive charges up here, they're going to attract the negative ends of the atoms or the molecules in the dielectric. They line up, and we will now have an electric field opposing the electric field from the capacitor. Vector diagrams are really cool. Let's see what happens. The blue line is the electric field of the plates without the dielectric. The dielectric now, the material got polarized and had an electric field going in the other direction, and typically it's smaller than the electric field of the plates without it. We now add these two electric fields together, and we have the electric field with the dielectric, or the net electric field, is smaller than it was in the beginning. So for a given applied voltage, the net electric field is smaller. This is very helpful for another reason, because if the electric field between the plates gets too big, you keep applying more voltage, the field gets very large, it could cause something called a dielectric breakdown in that space. A dielectric breakdown is very bad, because here's our two plates of the capacitor, and we talked earlier how you had a battery here. It would charge the capacitor, and all charge would flow through here. A dielectric breakdown means that this electric field is so powerful that charges, electrons, can now move through the gap, through either the dielectric or the air. That's known as a spark. That's how lightning works, or when you touch a doorknob after rubbing your feet on the carpet. Okay, lightning is a much bigger effect, but the same physics. So what we've done here is you have charge flowing where it shouldn't. That would destroy the capacitor. And also, if you were touching it or was near other circuit elements, it could harm them in addition. You're putting a lot of energy where it doesn't belong. You're getting a spark. This breaks, and people or equipment could get hurt. The dielectric material was originally neutral. Once it became polarized, more charge was now present. You had the charge on the plates, plus the charge induced in the dielectric by separating the charges positive and negative on either side of the material. Thus, the total charge in the capacitor increased. The voltage stayed the same, still connected to the same battery, so when we use the definition of capacitance, charge went up, voltage stayed same, capacitance of the configuration increases. That enables you to store more charge for a given voltage, and you can store more energy. An engineering benefit to the dielectric is that it insulates the plates from each other, and thus the distance between them can be made very, very small, and charges will not flow between the plates, such as sparks, but will flow through the battery, and it will work properly. So one way to make a dielectric is take two plates, positive and negative, stick a dielectric in between them, then roll it up so you can have a cylinder, which is a more practical, smaller shape to store energy in. And the dielectric will prevent any sparks or charges going between the two plates. Every material has a dielectric constant, kappa. That's a Greek letter, little k. We have a sample table of values here on the right. For a vacuum, K equals 1. K air is about 1. It's close enough. And if you have a dielectric present, we told you how it would increase the capacitance. The same formula for capacitance works, but we just add the kappa in there. So let's see, asbestos here would have a greater capacitance than bakelite, which would have a greater capacitance than paper. So any of these dielectrics, when you insert them, you can store more charge and have a greater capacitance than if you had air between the plates. And just a little simple summary, the larger the value of K, the greater the capacitance. Wrapping up our discussion of capacitors, we have three basic equations. One is the definition of capacitance. It's how much charge can be stored in a physical configuration depending on the voltage applied. We then derive the potential energy of the capacitor. See, we have U there. We found it was QV over 2. And then by substituting in different permutations of this equation, the definition, we got two other equivalent equations for energy. So for example, if we were given the charge and the capacitance on an object and we were asked to find the potential energy, we'd use this equation. If we had the capacitance and the voltage, this equation. This is true for parallel plate capacitors, as it depends on the specific geometry of the parallel planes. Unless indicated otherwise, kappa will equal 1. So if they give you a problem and they don't give you a dielectric present, assume kappa equals 1. And it's the area of each plate, or a single plate, you just use the area once, divided by the distance between the plates times the electrical permittivity of free space, which is a constant. Using these equations, we can solve many problems related to the voltage, the charge, the electric field, and the capacitance of a capacitor. What is the capacitance of a capacitor that has a plate area of 2.8 times 10 to the minus 3 square meters and a distance between the plates of 5 times 10 to the minus 3 meters? The capacitor has a dielectric between the two plates with a dielectric constant of 4.5. All the givens are given in the correct SI units, square meters, meters, and then the dielectric constant is unitless, so that's just 4.5. Here's our equation, and the addition here is that kappa in front of the epsilon 0 A over D because a dielectric is present. Here's our dielectric constant. We have epsilon 0, which again, you do not have to memorize. That will be on your formula sheet. Then put your area, cross-sectional area of the plates, distance between them, carry out the math, and get 2.23 times 10 to the minus 11th farads.